Hi there and welcome to a brand new Patreon course of Entagma. This course is called Particles and it will deal with particles. In this course you will learn how to work with particles inside of Houdini. You will understand dop nets as pops are living inside dops. You will learn how to use forces and wrangles to drive forces and to drive your particles. Particles is the bread and butter of visual effects, and that means everybody has to understand them. At the same time, they are the easiest entrance to the world of dops. So follow me through the episodes of this course and learn about the amazing world of particles inside of Houdini. Normally, I start a new course with a lot of theory, because I think theory is very important to understand the tools. But this time I want to do things a little differently. I want to start with a practical example. So follow me in this practical example while we try to peel off the paint of an object using particles. While doing so, you will learn a lot about particles, about the principles, and in one of the later episodes I will introduce you to the inner workings, of course, and how exactly a pop solver is working. But for now, we will just put down the effect. So without further ado, let's start. I already created a geometry object and called it particles. One level up, you see here is the particles object, and I loaded an OBJ file that I created in 3D code and exported as an OBJ file. And it comes in huge, because the scale of 3D code is 100 times larger than Houdini. So I just scale it down to bring it to a workable size, like so. So what we want to do is we want to have a rim traveling across the surface of this object, and where this rim travels, the paint is flying off and is revealing a metal object beneath. To do so, we have to first prepare our source object and then emit particles from a traveling rim that we have to create. So let's put down a VOP and create this traveling rim, this edge that travels across the object. So lay down a point VOP and call this animate, because we intend to animate this traveling edge. Make it visible and dive inside. The very first thing to do is to lay down an anti-alias noise, because we want to cover the object in noise. Connect the P port to the POS port. That means every point of the object is generating a noise value from the noise field that is created by this anti-alias noise node. And now, directly after that, apply a fit range, because the anti-alias noise node outputs values roughly in the range of -0.5 to 0.5. So let's fit the values between -0.5 to 0.5 to the range of 0 to 1. And let's visualize the noise quickly by connecting it to CD. And here you see the noise. If I get rid of the wireframe by pressing Shift W, you see the object now has a noise applied. Let's quickly right-click on the frequency port and promote this parameter. By doing so, we get this parameter here in the attributes of the animate VOP, and we can up the frequency here. So now we have this noise, but we want to animate the noise. The noise is values between 0 and 1. And what we want to do is we want to animate a parameter and just grab a small portion of this value range and remap this portion, say between 0 and 0.1, to 0 to 1. So let's create another fit operation. Fit range, and connect the output of the first fit, that is just normalizing the values, to this fit operation. And let's connect the output to CD. So now everything is default, nothing happens, but as soon as I change the source max down, you see that we now have selected basically only a little portion of the original value range. So what happens if we do this, but animate it? So let's do this. Let's create a parameter. And let's feed this parameter to the source min of the fit. That means by animating the parameter, we can tell which value will be the start for our new range. And now we want to have a certain distance from this value and want to use that as a source max. So let's add something to this parameter. And in our case, just let's add a constant. For now, let's put in 0.1 and add it here. Now we have two values. A value that can be animated and then an offset value that is 0.1 larger. Use this for the source max. So now we select the range between 0 and 0.1 and transform the range to 0 to 1. If we now go up, we find this parameter here. And if we move this parameter, you see that we now can animate the noise basically, or better, the value range of the noise, or we can select different values from the value range of the initial noise. And that is exactly what we want, because this animated noise will drive the particles later on. Well, this is very nice because it is a black and white mask that we can use to blend between two materials, revealing the shiny material underneath. We need a second mask that only selects the rim of this. So let's dive into the animate again, and let's do this. Let's put down a ramp parameter. The ramp parameter gives us the possibility to remap values using a curve or this color gradient here. Let's connect the output of this fit to the ramp, and let's call the ramp parameter ramp_rim, and let's switch the ramp type to float. Now connect the output of this to CD. Everything turns black immediately, and that is because by default the ramp is set to 0 on the entire range. But if we now pull up one of these values, you see we are back to the values like before, but now we can remap this. And by introducing a little spike here, like so, you can see that we are able to select a rim. So we just select a portion of the value range that should be white in the middle of the entire value range. And if we now animate our parameter, you see that the rim is traveling across the object. And this rim will be used to drive the particles. So let's bind the result of this ramp parameter. Sorry, that was the bind node. We need a bind export. So let's bind the result of this ramp parameter to an attribute, and let's call this attribute density. Like so. Density. Let's go up one level, and for now let's animate this parameter. So let's start with 0.8, say. Press Alt and then click in the parameter field to set a keyframe. Now go to 240 frames and move the slider up until nothing is visible anymore, and again press Alt and click in the field. Now we have 2 keyframes, and the noise is traveling over our object. Great. The next thing is that we want to append a normal node, just to give point normals to the object. So switch the normals type to points, and let's quickly check. Now we have normals. And now let's add a scatter node, like so. So this node scatters points on the surface of our object. Turn relax iterations off, because we want random behavior in this case. And now let's tick on density attribute. And as we set our rim as a density attribute with the name density, the scatter now picks up this attribute and only scatters points where the density is 1. So you see, if I now animate the entire scene, you see that points get scattered where the density is high. But if you have a close look, you see that the total count of points is always the same. And that means, while we have only very small areas with a high density, we have a very dense point scatter. And when we have large areas, like here, for example, the points are a lot more sparse. To counteract this, turn off force total count and instead increase the density scale, because the density scale makes sure that the density remains the same, no matter how large the area is that you scatter on. So let's say 10,000 for now. So now we create points in every single frame from this animated rim. And these points will be the points that emit our particles later on. To create particles, we need a dopnet. So append a dopnet, but there's a better option, because a dopnet, if you create one and dive inside, there's nothing in it. And of course we can create everything from scratch, but instead we can use a pop network. And the only difference between a dopnet and a popnet is that the popnet already has the relevant pop nodes inside. So create a pop network and connect it, make it visible, and dive inside. First rewind to frame 0, dive inside. And this is popland. So these nodes are necessary to create pops. We have this output here. We have the solver, and the solver is in charge of calculating the new particle positions from all the forces and velocities. Then we have this pop object that holds the particles, and we have this source node that is creating the new particles. So at the moment we don't have any particles, so let's go to the source and let's see. Here we have emission type, and emission type is set to scatter on surfaces. But over the very first context geometry port, we have points coming in, and points are not surfaces, so the node cannot scatter onto surfaces. Instead, switch this to all points. If you do that, and animate it a little, you see that now we get particles. That is because now all the points that are coming in are just cloned to be particles. You have white particles here and you have blue ones. And the blue ones are just the guide particles. So the blue ones are just the points that are coming in. You can turn them off here. So if you now press play, the simulation runs and a lot of particles are created. Because in every frame the rim travels, and where it is located, new particles are born. So the simulation will cover the entire object in particles. Cool, our very first particle simulation. But we want to do something a little different. We want to have them created, the particles, and then we want them to fly off the surface in the direction of the surface normal. So let's give the particles some initial velocity. To do this, we can of course set the velocity inside of the popnet directly to the particles. Another possibility that is maybe easier is to put velocity on the scattered points, because when the particles are created and cloned from these points, all the attributes are cloned with them, and velocity is no exception. So let's quickly create some velocity. Let's put down a wrangle, because this is the easiest way to create a custom velocity, and put it here, and let's call it set initial velocity or initial vel. Press Alt E over the editor and let's write v vector add v. V is the internal name for velocity. This is hard coded, so particles understand this, or the pop solver understand this as long as it's called v, and it should just be our normal. So the point normal, like so. Apply and accept. Rewind the simulation and see what this gives. And now you see, wow, we have streams of particles flying out of the object and flying off into midair. To see this better, let's quickly visualize the object. At the moment the object is gone because we turn it into points. So let's lay down a null and connect it here after the normal. That is our object. Let's quickly call this out, obj. And if we now go one level up, lay down a new geo, call it obj for object, dive inside, we can lay down a merge node, file merge, object merge, and we can point this object merge to the out.obj node that we just created. So it will bring in the object with all the attributes. And now if we go into the particles again, we have the object visible, and as soon as we make the pop solver visible, we have the object and the particles. You can switch to show all objects and you see both at the same time. The problem is that these velocities are too large. The particles are really shooting away like rockets. So let's scale them down. To scale them down, let's introduce a scale factor. So float scale, and let's say this should be 0.1 for now. And let's now multiply the normal with a vector composed of 3 times the scale factor. So set to create a vector, and then scale, comma, scale, comma, scale. Now we are multiplying the vector n by this scale here. Let's see what this gives. And now the particles are a lot slower, which is good. And you see they are created where the rim is traveling, and they shoot off into the air. Just where the rim travels. But at the moment it's all very ordered and not very interesting. So let's add a little randomness to this. For this, let's go into the popnet. Here you have the solver and the pop object and the source. These are all standard dot nodes. But these purple connections here allow you to introduce vec-based nodes, pop nodes. And one of these pop nodes is the pop wind node. Pop wind. So create one and just put it here between the source and this wire pops into here merge, like so. And this pop wind is basically a noise force. So let's up the amplitude of this to 2, and let's see what this gives. And you see now we don't have straight lines anymore, but we have chaotic wind behavior. At the same time, the swirls, this is using a curl noise, are very large, so let's say 0.2 to make smaller curls, and now it's curling a lot, like so. For now we can go down with the amplitude quite a bit, and now we have the stuff coming out and then curling very quickly. But they are still a little fast, so to make them slower, we can create a drag force. So let's lay down a pop drag right after this pop wind. And the pop drag has an air resistance parameter, and it will just slow down the particles over time. So if we play the simulation now, you see they start quite quickly and then get slower and slower and slower. That's a lot nicer. And now we want to kill the particles after they reach a certain age. Because at the moment they are flying off forever, and while we are emitting more and more particles, we increase our overall particle count. A, we don't see much because it generates this massive cloud of particles, and B, we have a lot of particles to deal with and everything starts to get slow. So let's introduce a pop kill. The pop kill allows you to tell particles to die and just to be removed from the system. Put it down here as the third node. To use a pop kill, we want to use vexpressions, so enable this vexpression here. And now I can write code here to tell the particles what to do. At the moment I have dead is 1 here, and that means all the particles are immediately marked dead. But we want to kill them only if they reach a certain age. So let's do this by introducing an if statement. If, and now comes another special attribute of particles called @age that stores the number, how old the particle is, as a float. And if this age is bigger than 1, then the particles should die. So now let's see what this gives. The particles fly off, and if they reach a certain age, they just die. Now this looks a lot more like it, because now the particles are emitted, fly off the surface, and then just die. Very nice. Let's go up one level and see everything together. And now you have particles being emitted from the rim of the object. We could go into this animate and use the output of this fit directly for CD. So instead of visualizing our rim, we visualize the mask now. And then you see you have particles coming from the rim and then revealing the object. Like so. So the basic effect is in place. We have one more thing to do, and that is that we want to deal with the size of the particles. At the moment, the particles are visualized as points in the viewport, and that is very fast, but these points are a certain size. They do not respect the p-scale attribute that is in charge of scaling the particles. To see the scale in the viewport, we have to use sprites, and we can do so by using a node called popSprite. So let's introduce a popSprite node, and let's put it here in front of the popWind as the very first node. If we rewind the simulation, you immediately see that all the points are now turned into these puffy clouds. That is a standard sprite. You can go into the popSprite and change this. As a standard, it is using smoke puff rad. That is a texture that is stored somewhere in the Houdini installation. And you can do something else. You can use sphere, and remember this name, sphere underscore mat.pick. That is a little sphere that is used for grains, and it is a standard texture from the Houdini installation too. If you do that, we have sphere sprites in the viewport. And you see they are large, and that is because we did not bother to set the p-scale attribute yet. So let's do this now. In front of the pop kill, let's introduce something very powerful, a pop wop. Because all the pops are implemented in Vex, there is no reason why you shouldn't have a pop wop to implement your own stuff. Dive inside, and this pop wop is really very similar to a sub wop. You have all the globals here and the outputs. It's nothing special. So if we dive inside, we see that this global node is giving us the age. So why don't we take the age and use it to set the p-scale value over time? Let's do this. Let's first append a fit to the age, basically to just clamp it. If the age is larger than 1, we want to have it stay 1. And then let's use another ramp parameter. And let's switch this ramp to spline ramp, and let's call it ramp underscore size. Like so. And now we can use this ramp to dial in the size changes over time, or over the age of each individual particle. And after that, I like to put another fit operation just to be able to dial in the final values. And to do so, I want to promote the destination minimum and destination maximum parameters. So now, the output of this setup goes to an attribute, bind export, and this attribute by default is called p-scale. It's another special attribute that is understood by the pop solver. As soon as I bind this, everything is very small, because now the particles start very small and then they start to get bigger very quickly. That is the behavior that this ramp is telling Houdini. But we can change this. What if we have them start big, like so, and then decrease in size over time? So that is exactly the opposite behavior. But of course, they are a lot too big. But because I promoted these two values from the second fit operation, I can now dial in the values. They should start with a size of 0.01, say, like so. And then they should get smaller over time. And look how beautiful this is. Because now they are starting big, and then they are getting smaller and smaller up until the age of 1, and then the pop kill sets in to kill them, because after an age of 1 they are too small to see, basically. And that gives us our basic effect. Now we have particles created from the rim, traveling across the object, and then scaling down to nothing, taking all the paint layer with them. So this concludes your very first particle effect. I hope you love particles as much as I do by now, and I hope you join me with the next episode that explains a lot more about particles. Thanks so much for listening. See you next time.